Hey guys, this is probably going to be your last lecture series for the semester. It's about chemical equilibrium. It's a pretty big part of chemistry. We saved it until the last topic, and these sets of notes are broken down into 4 sections. So up until this point, we have only been looking at reactions as going one way, right? We have reactants, they make products, and that's the end of it. But in the real world, reactants go in a forward and also a backwards or the reverse reaction. So this whole lecture series, we are going to be focusing on basically the forward and the reverse reaction and how do we know which way that it's going. All right, so let's start with part 1 of your notes, which is the introduction to chemical equilibrium, reversible reactions, and equilibrium. So let's go through some definitions so that we're all on the same page. A reversible reaction is going to be a reaction, and sometimes you'll see it abbreviated as RXN, so don't get confused if you see that instead of reaction. So it's a reaction that happens in both the forward and the reverse direction. So right down here, I've listed an example. So this is basically the dissociation or the breaking apart of, you guys should know what this is from the acid unit. So this is the acetate ion, polyatomic ion, right? 8, when it's an acid, change the ending to, hopefully you said ick in your brain. So this is actually acetic acid. And this is just showing the reaction of what happens to acetic acid when it turns into its ion component. What I want you to realize is now when we're looking at reactions, you're going to see a double arrow as opposed to the single arrow. And what the double arrow is going to represent, it's just going to tell you that that reaction can happen in both directions. We can either go from acetic acid to the hydrogen ion and the acetate ion, or the acetate ion and the hydrogen ion can combine to form acetic acid. All right, so then the second thing we're going to be talking a lot about in this unit is going to be equilibrium. So what is equilibrium? Equilibrium basically means when the rate of the forward reaction is the same as the rate of the reverse reaction. So when this happens, there is no overall change in concentration of the reactants or the products. Now, for those of you, I think most of you guys have taken biology. So if you think about it like homeostasis, right? Homeo meaning same. Body wants to keep basically everything at the same level. So we have all sorts of buffering systems in our body that will keep things in an acceptable level. It's the same thing with chemistry. So just like our body likes to maintain equilibrium, the reaction is going to shift in whatever direction it needs to maintain equilibrium. This whole principle is called Le Chatelier's principle. We're going to discuss that later. Those are actually the notes that are in section 4 once we get there. All right, so 1 is a pretty, I guess just an introduction to what equilibrium is. Let's go through part 2 and let's talk about the equilibrium constants and how to write them. So, equilibrium constants. What I want you to do is pay attention right up here to this equation that we have going on. It's just a generic equation. So I have little a and big A plus little b and big B. There is our double arrow that says it's a reversible reaction. And then I have little c and big C. And then little d and big D. What I want you to remember is that the A and the B are both going to be your reactants. All right? Your C and your D are both going to be your products. And then the small letters, you guys should remember, those are going to be your coefficients. So the small a is going to be the coefficient for our reactant A. The small b is going to be the coefficient for our reactant B. The little c is going to be our coefficient for product C. And then the little d is going to be the coefficient for product D. All right, so we're going to be talking about this thing called the equilibrium constant. Now, don't get it twisted. There are 2 different ways you can note the equilibrium constant. It can either be noted as Kc, all right, or it could be known as Keg. So if you see EQ, if you see either of those, you just need to know that they basically represent the same thing. So the equilibrium constant, which is either Kc or Keq, is going to equal the concentration of the products over the concentration of the reactants. Anytime that you guys see square brackets, you guys should remember this from the molarity, molality, and dilution unit. That's just going to mean concentration. So when we're talking about how to write the equilibrium expression, and this should make more sense once we start doing problems, but what you're going to look at it is you're going to look at it the concentration of the products over the concentration of the reactants. So if you take a look up here, we know that our products are C and D, right? So in the top of the equation, we're going to put the concentration of C times the concentration of D. Some of you guys might be like, hey, what are these little letters supposed to represent? Well, here's the deal. The coefficients are what you're going to use to raise your concentration to. So it'll make more sense, I promise, once we do problems. So it's going to be the product C raised to the coefficient of C, and then it's going to be the product D raised to the coefficient of D. And then at the bottom, it's going to be the same thing, but now we're talking about the reactants. So we have reactant A that's raised to the coefficient A, and then we have reactant B that is raised to the coefficient of B. Now, when I say raised to, I mean that it's going to be doubled, squared, quadrupled. All right, that's what I mean when I mean that it's going to be raised to that particular, let's say, power. It's going to become your exponent, if that makes sense. All right, so let's move on to looking at some of the rules. So if you want to know how to write these equations, you have to know what's acceptable and what's not. So like I said before, each product and reactant is going to be raised to the power of its coefficient. You're going to use the coefficients that are in the lowest common whole number multiples, which means if you have some sort of fraction, like if you have an oxygen, I know you guys hated them, that was in a fraction, you're going to have to turn it into a whole number for this to work. Other things you want to remember, only gas and aqueous are included. So a lot of you guys were asking me before, what does that little g mean? And what does the little AQ mean? What does the little L mean? And what does the little S mean? So the little g is going to represent a gas. AQ is going to be aqueous. If you see anything that has a little s, that's going to be solid. And then if you see anything that has a little L, those are going to be liquids. When we're doing these problems, you're only going to include gas and aqueous compounds. You're going to ignore liquids and solids. And we do that because their concentrations are fixed and they do not change. So the key thing I want you to take away from writing these equations, or I should say these expressions, is that solids and liquids do not affect the equilibrium. All right, so I know the vocab is always never ending. There are two more terminologies or two more terms that you guys need to know for this unit, and that would be homogeneous equilibrium and heterogeneous equilibrium. By now, you guys should know what homogeneous means. Basically means it's made up of the same thing. What this is that the reactants of products, if they're in the same phase, it's considered homogeneous equilibrium. And then for the second, we have heterogeneous equilibrium. So if the reactants and the products are in different phases, that's what hetero means, is different. They are in different phases, then that means it is heterogeneous equilibrium. We're actually going to go through a problem and we'll talk about whether it's homogeneous or heterogeneous equilibrium, and then you guys should have a better idea of what's going on. All right, so let's take a look at the problem. We have iron oxide plus carbon monoxide that yields iron, and then we're yielding carbon dioxide. So the first thing I want you to notice is notice all of the states, right? So the states, we have iron oxide is a solid, iron is a solid, carbon monoxide is a gas, carbon dioxide is a gas. So if you guys remember, based on the rules, only gas and aqueous are going to be included in our equilibrium expression. So anything that is solid or liquid, we're basically going to ignore it. So if you take a look at the problem, we're going to completely ignore iron oxide and we're going to completely ignore iron for our equilibrium constant. What that's going to mean is that we only have one reactant and one product that is going to determine our equilibrium constant, right? Because if you remember from before, this equilibrium constant equals the concentration of the products over the concentration of the reactants. I just put this over here kind of as a reminder as to what it's supposed to look like. So the equilibrium constant for this expression is going to be the concentration of your products. Our only product is CO2. that matters in our equilibrium expression over the concentration of our only reactant that's going to affect the equilibrium. And if you notice, the coefficients, they're both 1. So guess what? It'll be raised to the 1. So if you want to put it there, just so you know what's going on, you can. You don't have to put the 1 there, but I put it there so you could see the format that it basically is the products, or product in this case, that's going to be raised to the coefficient. So product here, raised to the coefficient, which is 1. And then reactant over here, right? That ends up being the concentration of the reactant that's raised to the power of 1 because the 1 is the coefficient here. So question, is it homogeneous or heterogeneous? Well, if you take a look at the states, iron oxide and iron, they're both solids. Carbon monoxide and carbon dioxide are both gases. So because we have different phases in our equation, that means that it is a heterogeneous equilibrium. So hopefully that homogeneous, heterogeneous equilibrium makes sense now. Let's go through an actual problem. So what does this mean in terms of trying to figure out what the equilibrium constant is numerically? So we're going to take a look now at what is the value of the equilibrium constant. So pretty much this is the same as the last slide. All right. We know that we need the concentration of CO2 over the concentration of carbon monoxide, and that will give us what our equilibrium constant is. So the problem that you have in your notes says at equilibrium there is a 0.12 molar carbon dioxide gas and a 0.02 molar carbon monoxide gas present. What is the value of the equilibrium constant? All right, so we'll set it up. Remember, our equilibrium constant is going to equal the product raised to its coefficient over the reactant raised to its coefficient. All we're going to do is plug in the numbers. The problem says that our concentration of carbon dioxide gas is 0.12 molar. And then it says that our concentration of carbon monoxide gas is 0.02 molar. So put them in the equation. Take 0.12, it's raised to the 1, so that is 0.12, divided by 0.06, which is raised to the, 0.02, which is raised to the 1, which is 0.02. You get an answer of 6. Now, some of you are going to be really, really happy because the equilibrium constants do not have a unit. So I can't hunt you down and say, where's your unit at? Because there is no unit for the equilibrium constant. There are only 2 things that we're going to be calculating that don't have units. I'm sure that some of you guys have already guessed the first one. We just covered it last week. Hopefully in your mind you thought pH, right? So pH didn't have a unit. It was just a number. It's the same thing with the equilibrium constant. All right, so hopefully that will help you guys just kind of understand how the equilibrium constant works. The next part of the presentation will be part 3 and part 4 of your notes.